Okay, this is our first lesson in the thermodynamics unit, and we're going to be talking a lot about energy. So thermodynamics, specifically thermo meaning heat, we're going to be talking a lot about what heat energy is. And a lot of this first lesson is just going to be learning to read potential energy diagrams that show the different amounts of energy in the products and reactants. So if we have a chemical reaction, we have reactants that turn into products. There's a certain amount of energy associated with the products and the reactants. And we can measure that, the amount of heat that the reactants have and the amount of heat the products have. And we can compare how does it change as the reactants turn into products. And we're going to graph that change. So here's a graph, and we're going to be kind of looking at this a lot. We have energy over here on the axis, and this is in kilojoules. And then we have progress down here of the reaction. So just from start to finish. There's no real time, but it's just what is the energy at the beginning, what is the energy at the end. And you can see there's two lines on this one. So what we're going to do is we're always going to have the reactants starting first, and then we're always going to end at the products. They're at another level. And then we're going to look at the difference between these. So right now I would say the reactants have 300 kilojoules of energy, and the products up here have 400 kilojoules of energy. And the difference between them is positive because the reactants are starting lower. So the difference is positive 100 kilojoules. That's the difference. That's how much energy change is happening from the start of the reaction to the finish where the products are. We can look at another one and say, all right, here the reactants are at 200 kilojoules, and the products, they're lower now, they're at 100 kilojoules. So now I'm going down 100, 200 to 100, and this reaction has negative 100 kilojoules of energy associated with it, the total reaction. Because here I have the reactants, here I have the products. We call that change from start to finish enthalpy. It's a measurement of the heat transfer in the reaction. And like we've been doing, it's the difference between the products and the reactants. Okay, so again here, I've got the reactants I'm starting with, and the products are at the end. So what is the enthalpy of this reaction? Well, it's going from here to here, starting up at 350 for the reactants, and I'm going down to 200 for the products. So the change is negative because it's going down. Negative 150 is the enthalpy. There's a unit for enthalpy, or a symbol rather. We call it delta H. Okay, so delta H, and H kind of talks about heat transfer if you want to remember it that way. It's the difference between the products and the reactants. And then there's two different ways we can measure this also. We're going to talk about an exothermic or endothermic, and we just want to know if the enthalpy is negative or is it positive. Is it giving off heat or is the reaction absorbing heat? In this case, the reactants are at 400 kilojoules, and the products are down here at 200, so the enthalpy is going down. The enthalpy is negative 200 kilojoules. If it's negative, that means it's giving off heat. Exo meaning giving off, exits, you leave. Heat is leaving. So there's a negative enthalpy. This is exothermic. Okay, anything that gives off heat, any reaction that gives off heat is exothermic. It has a negative delta H value. It can also be endothermic if it's positive. So if we go back up to the last slide, yep, that one's negative also. Let's go back two more. There we go. Just back up here to one of the previous slides that we looked at. The reaction here, this one went up, positive 300 to 400, positive 100. This one is absorbing heat. It's endothermic. Okay, so there's a delta H value, endo and exothermic. There's another point though that we call the transition state. There's a midpoint. It doesn't just go in a straight line from here to here, but it needs to get there somehow. So what is the path it takes to get from one point to the other? Well, it has to go through this transition state up at the top. Let me put my red line back in. I deleted it. It's supposed to be here at 250. Okay. So I have that dot up at top, and we're going to call that the transition state. The transition state is a midpoint between the products and the reactants, and it's exactly what it sounds like. It's a transition. So it's kind of halfway between the reactants and halfway between the products. The old molecule is starting to break apart, and the new one is starting to form. So the transition molecule is kind of a mixture of the two molecules with new bonds and old bonds breaking. And there's an energy associated with the transition state. So we're going to kind of make this ramp up to the transition state, and then it's going to go back down to the reactants. So now I have a third part. I've got reactants, products, and up here I have the transition state. Okay? So the transition state is kind of like a molecule, like the reactants and products. That has an energy of 400 kilojoules. The reactants have 200 kilojoules, and the products, I should put equal signs here so they're not negative, have 250 kilojoules. So even though I had to go up through the transition state, the change between the reactants and the products, delta H, was positive 50. So delta H is positive 50, and that is positive, so it is endothermic, absorbing energy. All right, and we kind of use the transition state as the reaction needs to go through it to get to the product. So that's the path that it takes through those 3 points. Let's look at this one. If I have my reactants here, my products at the end, the transition state up top, it's got to go through the transition state and back down to the products. So my reactants are at 300 kilojoules. My products equal 200 kilojoules. The transition state is at 500. My delta H value is going from products to reactants. It's this value here, 300 to 200. It's going down, so negative 100 kilojoules, and that means it's exothermic. There we go, spelling. Exothermic. All right. There's one more value here. Oh, we can look at reading the graph as well. One more value here called the activation energy. So if we have a graph plotted just much like we did, we have the reactants and the products and the transition state. Here we have our delta H value, products minus reactants, that distance. There's another distance we can measure here from the reactants up to the transition state. We call that the activation energy. It's the amount of energy needed to activate or start a reaction. It's very much like it sounds like. In order for the reaction to happen, we need to get up to the transition state. That's the middle. Think of it like a roller coaster. When you're going on a roller coaster, some chains take you up to the top of the hill, and then once you get to the top of the hill, what happens? Gravity takes over, and you race back down it. It's not until you get to the top that the ride actually starts, because that's when gravity takes over and starts shooting you down the ramp. And it's not until you get to the transition state here that the reaction actually starts, because my reactants are down here at 200 kilojoules of energy, but I need to put in enough energy to get up here. So if my activation energy in this chart is at if my transition state is at 400 kilojoules and the reactants are at 200, in order to activate this reaction, I need to go from 200 up to 400. I need to put in 200 kilojoules of energy. So the activation energy is this distance here from the reactants to get up to the top of the hill to actually start the reaction. All right, let's look at some practice. There's two more graphs here. Here's a graph, and I can start labeling it. I've got the reactants, products, and here at the top, the transition state. So I've got these 3 points. What do I know? So we're just reading the graph. The reactants have 250 kilojoules of energy. The products have 50 kilojoules of energy. The transition state has 300 kilojoules of energy. We're just reading those 3 points off the chart. And now I've got some other points here. The reactants are still at 250. This is at the same spot on the axis right here, 250. Going down to the products, that's my delta H value. So I'm going down 200 kilojoules, products to the reactants. Delta H is negative, going down 200 kilojoules. We know that's exothermic. And I can also measure my activation energy from here, the reactants, to the transition state. That's the activation energy. So in order for this reaction to happen, to activate it, I need to put in 50 kilojoules of energy, because it won't happen unless I get up to the top of the hill. So there's a lot of information in this chart, a couple different plots. We can also use the information given to graph it and find out new information if you know a little bit. So say we know the reactants are here at 200 and the products are up here at 400, and the activation energy is 300. This is where we need to be careful. The activation energy, you need to remember what it is. That's the amount needed to start it. So that's from the reactants up to the transition state. So I need to add, I'm at 200, I need to add 300 to get it to start. So 100, 200, 300. We'll put it here in the middle. That's the activation energy. From here to here is 300 kilojoules. That's the activation energy. Which means that the top here, the transition state, is at 500 kilojoules. That has a lot of energy. And my delta H value is products to reactants. And I'm just looking at the y-axis here. What's the difference going up or down? It's going from 200 to 400. So my delta H is positive 200 kilojoules. Which means positive, it is endothermic, and this reaction is absorbing energy. Okay? So we are, again, just to summarize it up, we are looking at the potential energy diagrams to see how much energy, specifically heat energy, is in the reactants and how much, comparing it to how much is in the products, to see how much energy a reaction gives off. If it gives off heat, it's exothermic. Takes in heat, it's endothermic. We'll talk more about what those mean later through the unit.